Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series in applied electronics. We are going through the section on optics, and in today's lecture, that is lecture number 18, we will go through interference and a portion or an introduction to diffraction. So, the contents of this lecture will be experimental setup for observing Newton's rings, determination of wavelength of a monochromatic source using the Newton's rings setup, and lastly an introduction to diffraction. This shows the experimental setup for observing Newton's rings. And what do you have now? You have got a source of light, a monochromatic source S, and the light coming from the source passes through a lens system L1, and it is incident on an inclined glass plate which is kept at an angle of inclination 45 degrees, and the light is partly reflected and travels towards the air gap that is present between the plano convex lens and the glass plate. You have the air film here. Obviously, at the center there will be no air gap, because the lens is in contact with the glass plate, exactly in contact, and the thickness of the air film, as I told you in the last lecture, will be increasing, as in the case of air wedge. Here also the thickness of the air film will be gradually increasing from 0 to some finite value. It keeps on increasing, the film thickness will be increasing, and depending upon the condition that will be satisfied by the light rays, either you will be having a constructive interference or a destructive interference. Let us see what are Newton's rings and how they look like and so on, and this is the experimental setup, right. And now we have to describe in detail the glass plate that you have here, and the plano convex lens you find here. The lens is here, G is the glass plate, lens is placed on the glass plate, and G1 is the beam splitter. That means it splits up the light partly to go to the this lens plate system, and partly it will be transmitted, and we are not concerned about the transmitted light beam, and we are concerned about only the reflected light beam. The reflected light beam will come back, right. It is going back, it undergoes reflection from the glass plate. You have the air film here, and M is the microscope through which you observe what you are going to see here, and C is the focusing lens or the condensing lens. S is the source of light, it is a monochromatic source, as I told you. This is the setup in detail, and we have, as I told you, a monochromatic source, and then the light rays are rendered parallel, and they are incident on a glass plate kept at an angle of incidence 45 degrees, and this is the glass plate. Okay. And you have got it is partly reflected, as I told you, and these are beautiful rings that was observed by Sir Isaac Newton, and hence named after Newton. You have got so called Newton's rings. One has to understand how and why these rings are obtained. The rings are alternately bright and dark. You see a dark ring here and a bright region here, bright ring, and then a dark ring, bright ring, and so on. And so at the center, this center here, right, and here for this radius it may be bright, and for some other radius the condition for destructive interference will happen, which will lead to a dark ring, and for some other thickness of air film the condition for brightness will be satisfied alternately depending upon the thickness of the air film. Either the condition for brightness or darkness will be satisfied. If the condition of brightness is satisfied, you will be getting a bright ring, and on the other hand, if the condition of darkness is obtained, then we will be having a dark ring, right. So, you will be having rings bright, dark, bright, and so on, and the radii of the rings are to be obtained. These radii of the different rings can be measured using the microscope. You have got the crosswire, using the crosswire, placing the crosswire at different rings, the radii of the rings can be measured, and you will be having the crosswire here. You see the rings here, you have the dark ring and a bright ring, dark ring, and so on. You see the crosswire. When you see through the microscope, you will see the crosswire, and you can the microscope can be moved either on the left or towards the right, and you should know as students of science or engineering, the microscope should be moved only in one direction, so that the error is minimized or error is eliminated. That will be only unidirectional movement, right. So, from left to right, you start from left, place the crosswire here, and to coincide with the maybe the nth dark ring or the nth bright ring, then take the reading, right. You have got a main scale reading, Vernier scale coincidence, you know the least count, MSR plus V, the Vernier scale coincidence to least count will give you the total reading. You take the reading when the wire is coinciding with the nth ring, then count n, n plus 1, n plus 2, n plus 3, then come to the n plus third ring, take the reading, then n plus sixth ring, take the reading, n plus ninth ring, take the reading, and so on. Similarly, go from left to you come here and go to the right, n plus 3, n plus 6, n plus 9, and so on. So, the diameter of the n plus the nth ring and n plus third ring, n plus sixth rings, the diameters of the various rings will be known, and that is what you are going to tabulate now. You will see now the reflected beam falls normally on the lens L placed under glass plate. Interference occurs between what? The interference will be occurring between the two rays. You know, one light ray will be, you see here, a light ray will be incident on this system, and it will be undergoing reflection at this surface at the bottom of the lens. Then what is the other light ray? Interference means there should be two rays, two beams will be there. One beam is the beam that is obtained because of the reflection of the light ray suffered at this surface, right, the bottom surface of the lens. The other light ray will be the light ray reflected from the top surface of the glass plate. This point should be made clear, should be understood. The point is, one light ray will be reflected from the bottom surface of the lens, right. The other light ray is the one that is coming from reflected from the top surface of the glass plate. Okay. The top surface of the glass plate is this point, bottom surface is here. So, this is the bottom surface, right. This is the top of the glass plate, this is the bottom surface, this is the top of the glass plate, and so the thickness of the air film will be changing, right. Now, this is the air gap, something like air wedge. So, here also you get a similar to air wedge, you have got a wedge shaped film. The thickness of the film will be, air film will be increasing, these two light rays will be interfering. So, this point is important. These are two light rays which will be interfering either constructively or destructively, and all of you know what is meant by constructive interference, what is the destructive interference, what are the conditions to be met, and so on. So, interference occurs between the two rays which I showed you just now, reflected from the upper and lower surface of the film. That means, from the bottom of the lens and the top of the glass plate. Okay. The interference rings are viewed with a microscope focused on the air film. I showed the microscope and you can see the rings, and the procedure now will be as follows. With the help of the travelling microscope, the diameters of a number of dark rings are measured. As I told you, the diameters are measured. The position of the microscope is adjusted so that the center of the Newton's rings at the point of intersection of the crosswires. You have the thing, the microscope is moved until one crosswire is tangential to the 16th dark ring. Maybe you start from the center, the center, right? The first ring, dark ring, second, third, fourth, fifth, and so on, go up to 16th dark ring, right? You have the crosswire to coincide, to be tangential to the 16th dark ring from the center, 16th on left, then 16 plus 4, 16 plus maybe 16 minus 4, 12, then 12 minus 4, 8, then 4, and so on. Then you come here, then you go to 4th ring, 8th ring, 12th ring, and 16th ring on the right hand side. 16th ring on the right hand side, if you take the reading, and the 16th ring you have taken the reading for the left hand side, this will give you the diameter. Suppose you take the first ring, you take the reading corresponding to, keep the crosswire here, and then keep the crosswire here. The difference between the two readings will give you what? It will give you the diameter of the ring, right? You keep the crosswire here, take the reading, keep the crosswire here. The distance separating these 2 points is nothing but the diameter of the ring. That gives the diameter of the, say, the first ring. So, the second ring. So, you are going to measure the diameters of various dark rings. The interference rings are viewed with a microscope. Then you take the readings, as I told you. You go to the 16th dark ring on the left hand side. The microscope readings are taken. Then the crosswire is made to be tangential, as I told you, with the 12th ring, 8th ring, this is the 16th ring, right. Then you go to the 12th ring, then you go to the 8th ring, then 4th ring. Then similarly, you go to the 4th ring on the right hand side, 8th ring on the right hand side, 12th ring and 16th ring. So, 16 is here on the right side, 16 is on the left. So, the difference between these two readings will give the diameter of the 16th ring. Difference between the two readings corresponding to 12th will give the diameter of the 12th ring. Similarly, this gives the diameter of the 8th ring. This gives the diameter of the 4th ring. So, you find the diameters of the different rings. Readings corresponding to the same rings are taken on the other side of the center. As I told you, start from here, come to the center, go to the other side. Okay. This is 16, 12, 8, 4, then 4 on the right hand side, 8, 12, 16. Okay. Now, I am going to tabulate the readings. Start from the number of ring is 16, you take the reading here left, okay. Then come to the 12th ring, then 8th ring, 4th ring, then go to the right side, take the reading here, 4th ring, 8th ring, 12th, and then 16. Okay. At the end of the job. So, now forget about the microscope, look at your notebook, then find the difference between these two. 16th ring reading that you are taking on the left, then on the right, the difference between these two will give you obviously the diameter of the 16th ring. That is what you are going to write here. The difference between the reading A that you are taking, B you are taking for the right, the A minus B will give you the obviously the diameter of the 16th ring. So, similarly, diameter of the 12th ring. Okay. The difference between these two will give you the diameter of the 8th ring, the diameter of 4th ring. Then you find the d square values. These are d, you find the diameter square. Okay. That you put on the next tabular column. Then you find dm square minus dp square. Dm may be the diameter of the 16th ring, dp will be the diameter of the 4th ring. Anyway, the point is you find the average of dm square minus dp square. Okay, the readings are tabulated, and the average values of dm square minus dp square is found for an air film. The refractive index is equal to 1. You know, for air the refractive index is 1. The diameter of the pth ring and mth rings are given as follows. You have dp square will be 4p multiplied by r into lambda. What is r? R is the radius of curvature of the lens. R is the radius of curvature of the lens. That is the important parameter. Similarly, dm square will be 4 into m into r into lambda. M is some number, maybe 12th ring or 8th ring, whatever be the thing. Okay. Then you have got the expressions now. Now, dm square minus dp square, obvious subtraction, you have got p minus m or m minus p. So, m minus p into r into lambda. Therefore, lambda will be equal to dm square minus dp square divided by 4 into m minus p into capital R. These things are taken to the denominator. That gives the wavelength of the monochromatic source. What is the aim of Newton's rings experiment? The aim is to determine the wavelength of a monochromatic source. What is a monochromatic source? A source which emits light of a single wavelength. In the laboratory, what is the monochromatic source? You are using to observe Newton's rings or to perform the experiment using air wedge. It is the usual sodium vapor lamp whose wavelength is, what is the wavelength of sodium vapor lamp? It is 58, 90 or 96. You know, sodium vapor lamp consists of, it is not strictly a monochromatic source. It emits light of two wavelengths, 58, 90 angstroms and 58, 96 angstroms. The difference being only 6 angstroms. For all practical purposes, it is considered a monochromatic source with the average wavelength of 58, 90, 96, average is 58, 93 angstroms. That is the wavelength of the sodium vapor lamp, that is the wavelength of the monochromatic source, that is sodium vapor lamp. This is a lamp where I am sitting here, is a mercury vapor lamp, it is a white light, it is not a monochromatic source, whereas a monochromatic source is a source which emits a single wavelength, but whereas the white light has got different colors, WebGR, right. Anyway, substituting this value of R should be known. How will you calculate lambda? This dm square and dp square have been tabulated, right. This is what you have got. From the experiment, you know dm square and dp square value, average value you have taken, right. These are known. That is what you have done so far. So, this is known. Now, m and p are known. So, m and p are substituted here. R should be known, that is the radius of curvature should be separately found out. Radius of curvature what? Of the plano convex lens, that should be known. So, the radius of curvature R should be known. Substituting this value of R in the average value of dm square and dp square that you got in the numerator with m minus p is equal to 8. You take m minus p equal to some 4 or 8 in the above equation, lambda is calculated. So, you have got dm square and dp square with having m minus p equal to 8. So, m minus p is known, you know R value, calculate the lambda value. This is an important experiment. The Newton's experiment is an experiment wherein the formation of rings are explained on the basis of interference of light, that is light consists of waves, right. You have got the wave nature of light. So, the phenomenon of interference can be explained only on the basis of so called wave theory of light. We have been seeing so far the phenomenon of interference. I am again repeating, we have the wave theory of light. Prior to the arrival or the the introduction of wave theory of light, we were believing light to be made up of corpuscles. That is what Newton thought. The corpuscular theory of light propounded by Isaac Newton, light consists of particles of light, right, particles, that are wave packets, that is no longer valid. Light actually consists of waves. The wave theory is important. Without wave theory of light, you cannot explain the phenomenon of interference. Similarly, other phenomena which we are going to deal with, such as diffraction and polarization, these new phenomena can be explained only on the basis of wave theory of light, right. So, that should be borne in mind. The wave theory of light should be definitely brought into the picture, then only you can understand or you can explain the phenomenon of interference, similarly diffraction and polarization. What is meant by diffraction? This is another another phenomenon, right, it is a very important phenomenon. What is meant by diffraction? Now, supposing I have a beam of light coming from a source, you have got a beam of light here. Now, there is an obstacle placed here in the path of the light beam. The light is coming here, right, this direction. Now, there is an obstacle placed, then whether light will be coming here. The question is, will you have light here? The obstacle is something in a cardboard, a board here. It is not transparent, light will not be passing through it, right, obviously. So, will you have light here? There will be no light, right. Now, let me now ask you the question. Suppose I sit here, you consider this a wall. I am sitting here, okay. This is a wall. This is a veranda, okay. I am sitting here and you are sitting in this room. I am sitting in this room, you are sitting in this room. When I speak louder, when I talk louder, will you be able to hear? You are able to hear. You are having the habit of overhearing others. You can overhear what I am talking. That means sound waves which are made here are able to pass through the next hall, because sound waves show the phenomenon of diffraction. What is diffraction? It is the bending of the wave. If you make sound here, I am sitting in a room, right. There is a wall here, I am sitting in this room, the neighboring person is sitting in the adjacent room, but whatever I talk you can hear, because sound undergoes diffraction, or sound wave exhibits diffraction. What is meant by diffraction? Diffraction is nothing but the bending of waves. Diffraction is nothing but the bending of waves. The light waves easily bend. The wavelength of the waves are so large and they bend. Similarly, light waves also bend. Supposing light is made up of rays of light, then there will be no bending at all, right. Supposing you assume the light is made up of rays. According to Isaac Newton, light consists of rays. They are made up of particles. So, if you use the particle aspect, the rays of light will not bend. Now, I am going to show in the lectures to come that light also bends. The bending of the light beam can be explained only on the basis of assuming light to be made up of waves. By assuming light is made up of waves, you can explain the phenomenon of diffraction. Diffraction is nothing but the bending of waves around an obstacle or through a hole. I can have a hole and pass light, and then bending of the light beam around obstacles is known as diffraction. It is a very important phenomenon. Because of diffraction, you see the colors, right. What is this? This is your CD, the compact disc. It shows different colors, right. When you have it in white light, it shows different colors. These are the colors which you observe, the bluish color, the reddish color, green, and if you change the direction, the plane is tilted, you see the different colors, and the colors that you observe are due to the phenomenon of diffraction. I told you in one of the earlier lectures that about colors of thin films. When oil is spilled over on a road, you see colors in a water than oil film, and colors are due to interference. But these colors that you get on a CD, you got CDs, you may see a halo of color arranged around street lamps on a foggy night. CDs and DVDs will show beautiful rainbow patterns if held up to the light. This is due to the phenomenon of diffraction. Sound waves diffract when they pass through the doors or move past the edges of walls. That is what I told you. You got a wall here, sound waves will undergo diffraction. Similarly, light undergoes diffraction. That means light behaves like sound waves, right. They are different in nature, but anyway, you should associate wavelength nature with light radiation, then only you can explain the phenomenon of diffraction. If you are in a room with the door open, you may be able to hear someone speaking outside, although you cannot see them. You are in the next room, but still you are able to hear me, because of the fact that sound undergoes bending of the sound beam. So, sound waves undergo bending, or they are able to your obstacle is there, the wall is here, but still in the veranda somebody can overhear. Similarly, if you look at a street lamp through an umbrella, you will see an interesting pattern of colored dots. All these effects are due to the property of diffraction. They show that the diffraction effects are greater for long wavelengths. The wavelength is large, means, as I told you, sound waves are having longer wavelength, that is why they easily undergo diffraction. So, the diffraction effects are greater for long wavelength waves. The diffraction effects are greater for small hole. A hole should be, if you drill a hole, the hole should be small. Or I will come to the case of diffraction, grating. Anyway, whatever you think, the hole that I will be showing, or the a wedge, whatever that you are having, should be small in size. The next diagram shows a wave bending a barrier, right. You got a barrier, you got an obstacle, right. The gap should be small, as I told you. If the gap is small, the profound phenomenon of bending is seen, right. You see the curvature is large, but here the curvature is not so large, because the gap is a long gap. You see a gap here, the sound wave is coming here, the light waves are coming here, or even sound waves are coming here. The gap is large here, the gap is small. If the gap is small, the effect will be profound. The diffraction effects are most obvious when the object of or aperture causing the diffraction is similar in size to the wavelength of the waves. The wavelength of the waves and the object size are of the same wavelength are similar, then only the diffraction effect will be profound. I think at this point I will just give you a few words. You will be hearing about X-ray diffraction, or you have heard of X-ray diffraction, neutron diffraction, electron diffraction, and in the years to come, or you got scanning electron microscope and so on. So, the phenomenon of diffraction is present or will be understood only if the condition is the wavelength of the wave and the size of the obstacle or the object to be studied. It may be distance between two atoms to be studied by X-rays or by neutron beam and so on. The distance between the two atoms and the wavelength of the X-ray beam or the wavelength of the neutron beam, they should be more or less equal, more or less of the same magnitude. Then only diffraction effects will be profound. That is the reason why you talk of X-ray diffraction and so on. So, the diffraction effects are greater for small holes. This explains why it is possible to hear sounds and receive radio signals, even if there is something between you and the source of waves. Let me now pass on to summary session. The summary goes as follows. Newton's rings experiment allow us to determine the wavelength of the monochromatic source by measuring the diameter of the rings and knowing the radius of curvature of the convex lens. Diffraction is nothing but bending of light beam around an obstacle. The questions are: 1. Explain the experimental setup to observe Newton's rings. Question number 2. Give the expression for the wavelength of the monochromatic source in Newton's rings experiment. What is meant by diffraction of light? With this, we come to the end of this lecture. The remaining things we will see in the lectures to come. Thank you.